I am a, okay. I, I'm old. I was in your place spot many, many years ago when there wasn't training in informatics. There was one program. It was the Stanford program. I did not go through that program. So I'm not formally trained in informatics. I'm sort of self-taught. How did that happen? I was a biomedical engineer. So I was very happy to hear that one of you is a BME. I was actually a BME in the first undergraduate BME program in the United States, which was actually at Texas A&M. And we had 8 graduates, 7 of whom went to work for the DoD, and I ended up not doing that. The reason because of that, and to get to the kind of travel story, is because at the time I was not a US citizen. So I actually was born and raised in South America. I was born in Brazil because my dad lived there. He was a graduate from Georgia Tech as an engineer and got a job in Brazil. So out of our 5 brothers, my 5 siblings, we have 2 Brazilians, 2 Peruvians, and 1 Chilean. But we don't look like it at all. So I've been around the world a little bit that way. And it definitely is a different perspective. And I'm happy to hear most of you really like to travel outside the US because I think it's totally cool. And it's great to see the world. I would encourage you not to wait till you're too old to go out there. Do it as you can as you're doing it because it's awesome. So I went to medical school after working for EDS for a year. That was electronic data systems, where I had the pleasure of writing something called job control language for the mainframe, which was terrible compared to having finished a dog lab in physiology at Texas A&M and developing, like, figuring out how dialysis machines work and how to design one. And so I decided I really wanted to go back to medicine. So I got a job at a cancer lab. And I ended up, they needed somebody to program. So I ended up programming an instrument that would heat up tumors, and it had to be programmable. So I wrote it in assembly language programming back in the day. And at that point, I kind of became hooked on computers. So ever since then, I've been a sort of computer person, but I went to medical school after that. The guy that I worked with insisted that we went on wards to see patients with him because he was partly, an academic, did clinical medicine, but also saw did experiments, research new drugs and that kind of stuff. And then that was interesting because it was problem solving. And those of you who are engineers, chemies, BMEs, engineering is about problem solving, and medicine is definitely problem solving as well. It's just a different style. So I was hooked, went to medical school, came out, did internal medicine residency at UC Davis, and then stayed as a faculty member at UC Davis. And then I did my research in computer science because at the time, the combination of medicine and computer science was kind of unusual. So that was an advantage for me to be kind of a niche. But I'm not formally trained in computer science. I really wish I had done a degree in computer science. I love computer science, many aspects of it, but just never had the time to do it. So I spent 24 years as a faculty member there, and then came here 4 years ago as a clinical research information officer here. But I've been building software with a team in public health for 17 years. So the birth and death registration systems in California are systems that my team has built with me along as a chief informaticist and designer, and I've worked in that space. So I have kind of this technical side. I know the technology pretty well, probably better than a lot of my colleagues that are doctors. And I know the doctor side, but I don't see patients anymore. So I stopped doing that because I just don't have the time. But and I really miss it. But it just once you don't practice enough, you have to think to yourself, am I really being am I the safest doctor they could get if if you practice medicine as a hobby? I certainly wouldn't want a hobby doctor, somebody seeing patients every, once a month. So I decided to stop seeing patients. So that's me. Yes, eu falo português muito bem. Eu creo que sim. And yes, I was crushed last weekend. So those of you who are soccer fans, Brazil lost to Argentina, but I was very happy that Messi actually, helped Argentina win. So, but yes, I was crushed. Yeah, I do speak Portuguese. I had to read and write it and all that stuff. So, all right. So what are we going to talk about today? We're going to talk about acquiring and preparing clinical real world data for analysis. And we're going to talk about what that means What do I mean when I say real world data? And I hope we can go through some of the stuff. I'll show it to you in real time, but we don't have enough time where each one of you can download software and connect. And Lauren has been in one of my classes where we did do that, some of that. We did a deep dive, and we did a deep dive into database technology and data modeling and that kind of stuff. So there's that course is available. And I've had even undergraduates take courses with me. I'm not the harshest professor, and so I think it's not a super stressful class, but I think you do learn. So I am teaching a natural language processing class coming up. So if anybody's interested in that in the fall, you can take that. For those of you, these are, you guys are all interns, so many of you are from away. So you won't be able to take that class. But anyway, so we're going to cover a lot of stuff here that I hope will be helpful. All right. So what are we doing today? Well, basically today I'm kicking you off in your career as what we would consider a data wrangler. And why is that? Basically, wrangling data is something that you'll often have to do in our area, known as informatics or information science. The computer science students in the class do, know this, but oftentimes, when you're a student, you're given data sets for a class exercise, and they've been sort of curated, and they're fairly easy to deal with because the professor like myself wouldn't give you data that you had to kind of, fix, because the whole point is for you to learn a technique and not have to mess with fixing data to then get to that. But the downside of that is you then are not exposed to having to fix data or wrangle it, or deal with data in the real world. I have a colleague of mine from Davis, Dr. Levinson, who coined the term for me, DIRDA. And so he calls healthcare data DIRDA because when it's coming out of the healthcare IT systems, it isn't curated and in a way that is easy to analyze. Sometimes you have to manipulate it. So that's what everything, what we're going to talk about today is about some data sets and where you can get some, and the tooling that you might need and how to do that at a very sort of basic level. So this is your career as a data wrangler. So the first thing is, what is RDW, as I call it, real world data? It's a term that you'll hear more and more in healthcare, in particular around regulatory things in the FDA. And for the longest time, the FDA only accepted data for the purposes of approving drugs. You have to give them evidence that it works. You had to do that with a prospective clinical trial where you captured not only was it the drug being given to patients, but you had to capture the data prospectively in a very controlled fashion. So the data is always correct, it's pristine, you can analyze it, it's very reliable. The FDA has now agreed that in a fair number of cases that you can deliver to them data from the real world, meaning EHR data that really wasn't intended to be prospectively collected in a controlled fashion, but is the result of a drug being given and documentation as to what's happening. And that's unprecedented. The FDA has never really done that before. And they use the term real world data. So we're going to talk about, what does that mean? And there's a few people that tried to define it. It basically is DIRDA, but we'll talk about it. It's not just EHR data. So you're going to get familiar with categories of RDW, or real world data, loading data into a tool that you can use to perform queries or look at the data, and then to peer in, and this notion of quality control checks. And I have an example here. So you don't just take the data set and that it's correct at face value. You want to verify that. And how do you verify that? You have to look at the data. And how do you look at it? You have to query it. You have to try to visualize it. And we'll talk about that. And then some tips and tricks. I don't think I'll be able to get into that very much. I'll mention them as to what they are, the Charlson and the Alex Hauser. But I think those are probably not that helpful for you. And then we'll talk about interesting publicly available health data sets, which you're probably not aware of. and this sort of movement called open data, which I think is pretty cool. It's been around for about 8 years now, and I was part of it, as somebody in the public health domain. But before we get there, why are we doing this? Now you guys, I think of all people, are okay with getting your hands dirty kind of thing and being in the lab, and like, if you were in a research lab, taking care of the animals, or cleaning the lab and pipetting and things like that. When I talk to faculty members, even assistant professors, sometimes they're like, well, I'm going to hire somebody to do that. The reality is you have to know how to do the stuff yourself. And most of us who start in academic careers have to do the basic stuff. Why am I showing you this? Well, first off, I want you to be aware that it's the 100-year anniversary of the discovery of insulin. In fact, July 30th, which is 15 days from now, was the first dog that was treated with the compound that later was to become known as insulin, and basically made an incurable fatal disease that kids would die in their teens, a curable disease, and one that would not cause death, in their teens. So Lauren will tell you I'm a kind of a history buff, and I just wanted to highlight that. And I'm also showing you that Dr. Banting is the one on the right here, and Charles Best is the one on the left. Charles Best was a medical student. I was given to Charles Banting for the summer to help him out. They purposefully gave him the worst student in the class, and they also gave them the worst lab to work in because he didn't have any money, he didn't have funding. So he did that, and they had to buy their own dogs. And there's one dog that they was the one that kind of showed them that what they were doing was actually treating diabetes correctly. And this was sort of the holy grail. They got the Nobel Prize for this. Banting did. And I'm not going to go into the whole story. I encourage you to read about the story because it's a wonderful story about scientific discovery by a family practitioner who had no business being an investigational researcher, and was actually shunned by many people. Very similar to the woman who I think will probably be credited with a Nobel for having invented the mRNA as a vaccine. Same kind of notion here. But anyway, just so you know, I'm just raising your awareness, and the fact that they themselves recorded their own data. There was nobody doing that for them. They had to, if they had computers, they would have programmed them themselves. So nobody's going to, in a lab sense, nobody's going to pipette samples for you. Nobody's going to take care of the lab animals for you. Nobody's going to go to note taking and charting for you. So you have to really be able to wrangle the data in an informatics sense if you're an informaticist yourself. So why focus on real world data in the session? It's the data that will require the most wrangling skills. It is the dirtiest data, or the most inconsistent, or the one that you really have to look at the most closely. It's also the data you're most likely to encounter first in your biomedical informatics career, without a doubt. It is the data that requires not only wrangling skills, but domain knowledge and insights into things like how was it captured? What did the electronic health record look like visually when the clinician was doing something, if they had a choice? And was it really, did something in the user interface influence them to do something? And we'll talk about some pitfalls. And the data that we see that we typically use in healthcare that we have to wrangle comes from not just the EHR, but comes from lots of different places. And I think as we go forward, we're going to see some of it coming from wearables. We already see that. Sensors that are on your body. The person in the BME who's a BME student, it's a super exciting time. When I was a BME, there was one program with an undergraduate BME degree. Everybody got masters and PhDs and went to work for NASA or GE, doing cockpit design and things, which is all cool. But, as an undergraduate, it was sort of like your job was clinical engineering and checking out equipment. That wasn't too exciting. And we always knew that there would come a time when there would be sort of these wearables, wearable sensors that would give you real-time data. And of course, now they're here. And it's not just sensors on your body, but sensors in the environment, and integrating that with your location. And if you're an asthmatic, you're in a high, danger place for asthma because of the smoke, and the app would tell you, hey, you can go somewhere else or stay inside, that kind of thing. It is here. And it's a confluence of, technology, smartphone, wearable sensors, and the engineering BME student will know, because they do electrical engineering, that the power requirements of a sensor on your body are such that, you don't want to be carrying or lugging around a battery. It's one, you want to try to make it like something that can attach to your skin like a Band-Aid, but then how does it get power and how long does it last? And all those kind of electrical engineering issues, are relevant in that. And we're at a point in our technology cycle that we can actually put things with a fair amount of computational capability as a Band-Aid on your body, and have it be there for a week or two. So the technology is pretty amazing now. So that's great, and we're going to see more of that. We have telemedicine, we have video, audio, all sorts of stuff happening now. So it's a very heterogeneous data environment with a lot of data. So this is the definition of real world data. These are different organizations, and I like the last one there, which is an umbrella term, basically that means that this is data that comes out of routine clinical practice. It's not coming from a process designed to give you clean data. It's a process that's designed to provide care, and because of that, we don't have structured data, as we call it, all the time. We have some unstructured data, clinical text notes and things like that. And there's a fair amount of key information that's in a clinical text note that you have to extract to be able to compute with. And that's the whole reason for NLP. And that is, that's not as straightforward as just getting data out of an Excel spreadsheet. When it comes to real world data, there's non-real world data, which we mean to say is structured data that somebody's putting into a computer. And if they put in the wrong number, it tells them, hey, I think 50 is nonsense. Are you sure you want to put in 50? Where if you're in a clinical practice, maybe 50 is fine, and the researcher has to deal with that value later. And so the EHR data is definitely real world data. Claims databases or billing data, social media, things like that. Things in the research side, when you're doing a clinical trial, tend to be very curated, controlled, and non-RWD kind of. So anyway, I hope I made the point of what is real world data, RWD, which is a term you'll hear about. So the FDA, the Cures Act of 2016, required the FDA to evaluate the use of real world data in discovering real world evidence to support the approval of a drug. Never been done in history. Probably would not have been something the FDA would agree to do without pressure, but it's a game changer. So now we have, especially when we have EHRs, we've gone from an adoption rate of 30% of clinical practices in pre-2007 using electronic healthcare record systems for practice to 98% now. So that, the HITECH Act that infused money to pay doctors to adopt clinical, systems to do all their stuff, charting and everything, electronic health records, has succeeded. But to do that, we needed to make it easy for them to do it. And so they need to be able to just type whatever they want and say whatever they want. That doesn't lead to controlled computable data, clean data. So that's why the FDA was always a little leery of that. Well, here we are. The FDA had to look into it, and they said, hey, the data is good enough. And in fact, real world data is behind the approvals of the COVID vaccines we see, and is part of the reason for the speed at which they've been approved for emergency use. I know there's a lot of debate about, are they safe or whatever. The fact remains that over 150 million doses of some form of, usually 2 vaccines, but now a third one, have been given in this country. And yes, there have been deaths. There have been about 9,000 deaths from the vaccines, but they're effective. People have died of vaccines all along, and the death rate from the vaccine here is not any higher than any other vaccine we have. It's just that it's front and center in the news because, it's the pandemic is relevant to everybody. And so it's getting an interesting dose of sort of exposure, but this is no different. It's actually quite safe. Nevertheless, and how did it get approved so fast? The approval happened in about 6 months. The vaccines were tested, and all that data was actually in EHRs and submitted, in real time to the FDA. Again, it's not a very complicated trial. It's not like we're doing chemotherapy. So, it's a shot. So, that also helped. The data points weren't significant before you could easily see that it was effective. Those were getting vaccinated. Those who weren't vaccinated had a much lower rate of COVID infection. So, so that's an easy kind of thing prospectively to kind of see, because it involves just a COVID test, and after the vaccine. And so just that little data point going, but nevertheless, the speed was pretty phenomenal. We've never seen anything like this in history. The normal knowledge turn rates, as we call them, from something new to being put into practice is usually 17 years in healthcare. Now, vaccines are usually about 6 to 7 years. This was done in 6 to 7 months. So, in terms of at least arriving at the fact that it wasn't something that was catastrophically bad and didn't work. So anyway, I just want to highlight that. You'll hear about that real world data that we see from an EHR. What is the kind of data we see in electronic healthcare record system? So I think as interns, I think we have a medical student here. So you've probably seen healthcare data up front, in person in electronic healthcare record system. But you're the only one. So most of you have not actually seen healthcare data, I would presume. Tell me otherwise, but I think I suspect that most of you have not. If you haven't, raised your hand digitally, and just so I can verify. But I think most of you have not seen healthcare data, or know kind of what data is in the chart, electronic chart. Am I right? Most of you have not. Am I correct? Anybody?
Yeah, no one raised their hand, so looks like you're right.
Yeah. Okay. So the kind of data,
maybe have.
yeah, the kind of data we see, there's demographic data. When you go to the doctor, you kind of, that they know your age and, your gender, your ethnicity, height, weight, that kind of stuff. That's all being put into electronic healthcare record system. So that's in there. And there's laboratory data. So if you've ever had a lab test done, the results will be there. Those results come out of a machine. The machine spits out the number, so nobody's having to retype that. And the machine spits out also the range, rate, the normal range, and the units of measures, we call it. The units of measure is an important aspect, because sometimes we have to convert between two different units. So that is all coming out automatically from the instrument into essentially the electronic healthcare record system. We have radiology images. We're not going to talk about those today, but with those images come reports. So the reports are actually narrative text. Those have to, if you're going to do anything with those, it's going to have to be natural language processing. So those, there's no button that says that's a pneumonia, that's a so-and-so. That's written out in a report, and then we act on that as doctors by prescribing things. But the fact that it's a pneumonia later gets recorded in billing data, as we call it. When somebody charges for that, for you being in the hospital, or and getting the antibiotics and everything, when the health plan gets the bill generation is being done, and then somebody is saying that really is this particular pneumonia, and the pneumonia has a code from a coding system, and we'll talk about that. And so that's when it's formally, oh, that's computable. I can find out how many pneumonias I had by going into the database and querying how many of those codes do I see in patients. But when it's in a radiology report, you can't do that. So just kind of, there's a difference. If somebody's been in the hospital, they have vital signs, they have waveforms. Again, the biomedical engineer, chemical engineers as well, I'm sure you get to see things that are waveform, that are digital, signal processing kinds of things. That's what you see. We don't deal with that in the EHR. It doesn't come in as a waveform. It doesn't come in as, in numbers that you then plot. We get a picture. Like an EKG, we see it as a picture, even though it really was a digital acquisition of data, through a analog to digital conversion, with the sensor and voltages and whatnots, and later becomes a number. And that number then is used to create the, for the plotter to create the image. What we see is images. So we don't actually get all of those numbers. That's not something that's done, even though it's available in the EKG machine itself. We don't see that in the record. Medication list, so we know what they've taken, when it was given, and if they took it in the hospital and the timing. And then diagnoses, as I mentioned. When does that happen? It usually happens at the end of a visit or the end of being in the hospital. They're going to bill the insurance. A person known as a biller goes through the chart and goes through and sees what was done, et cetera. And then they go, oh, it was an appendectomy. So the surgeon did an appendicitis. So the surgeon did an appendectomy. The ED diagnosed appendicitis after they did a CT scan and an exam. And each one of those things is being billed and they get a code. And so oftentimes we call that administrative data. That's what is computable in a clinical, in the EHR. And I'll show you that. And then there's notes. As I said, when somebody is admitted to the hospital, there's a history and physical. There's daily progress notes every day in the hospital. There's operative notes if an operation's done. The entire description of the entire operation is essentially dictated by the surgeon, step by step. There's two reasons for that: medical, legal, as well as just making, when somebody sees you later and they're a surgeon too, they can look at the note and know exactly what the surgeon did in your body. And sometimes that's important because there's certain procedures that are done, but they could have decided to do two different things, A or B, and that will only be known by reading the note, even though the procedure is the same. Did they tie that vessel off or this vessel off? Did they hook this to that or what? That's all said. What kind of graft material they might have used, for example, when they're doing an aneurysmal repair, things like that. That's all in the op note. That's not something that's coded. So you couldn't really say, how many patients have I done an aneurysmal repair with this kind of material? Unless I went to the billing system or the billing data and checked to see how often was that ordered, paid for, that particular mesh, for example, or whatever it might be. So because of that, what you see oftentimes in this data are what we call cookie crumbs. They're not the cookie, they're crumbs, like electronic crumbs that you kind of have to follow and make inferences about. And that's a very common thing. So bottom line, seeking and obtaining data is important. So we'll talk about that. The formats that you'll see, most of you probably heard of the term CSV. I don't know if you're aware of what it means, but it means a separated value file. It means that it's the only difference between that and a tab delimited file. It's a tabular form. So here's a table. This is actually the result of a database query, but it gives you the idea. Here's the table. These are things in columns in a CSV in a file, a flat file that you could open with even a text editor. You would see this number 21 with a comma between that one and this number and a comma. So it's using the commas as an indicator of the beginning and the end of a column. That's a problem when the content itself has a comma in it, right? So if the value of the data that's in there is actually a part of a sentence, let's say, so column 1 is a number, column 2 is a number, column 3 is a phrase, which has a comma in it, the computer could get confused because it doesn't know, well, okay, now I've got 4 columns. I was told I had 3. So oftentimes what you see is those values are wrapped around with double quotes on either side. So what you would see is quote 21, quote, comma, quote 22, quote, comma. And then when it's that phrase, it's quote, blah, 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 comma, blah, 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 quote, and then comma. And the computer knows that any commas inside the quotes are to be ignored. So just so you know what a CSV file, and the CSV file, Excel can produce this, you can take an Excel spreadsheet and output it as CSV. You can also open one, which is essentially importing it into Excel format from a CSV file. So the very common way of sharing and giving you data in a tabular form. There's a relational database. Sometimes you'll access a relational database. And I'll show you that hopefully, where it's tabular data. And then of course you can open files yourselves with programming language. So there's lots of ways to do that. What do you see in these, systems when you look in? So this is a survey of multiple of these systems and their clinical data repositories. So EHRs, So this is the kind of information you see in there. Like I said, demographics, super easy, diagnoses, procedures, et cetera. Once you get down to text notes, 30% of them didn't actually even have the text notes in the data repository, and it kind of falls off. That is the system that is used to store the data for analysis, which is separate from the EHR itself. You never want somebody to do an analysis query in the EHR that's being used to prescribe medicine or whatever. Why? Because if it's a big query that slows down the machine, the other people prescribing are having to wait 10 seconds between clicks. That would be intolerable. The other is that the data itself is arranged differently in both systems. It's arranged optimally to do transactions in the transactional system. And in the analytical system, it's arranged so that it can be doing analysis across patients. And the data is actually arranged differently. So those are two reasons why a warehouse, as it's known, is typically separate from the EHR. And when we do analysis, we're taking data out of the warehouse, and the EHR is giving the data to the warehouse every minute or every day. There's some update pattern, but you're getting it out of the data repository. And then when they do that, they either give you access to it as a database, or they burp out the files as CSVs and then say, here you go. So when you get those files, you have to do something with them. I did want to highlight, sometimes you'll get data that is mismatched, like from two different hospitals, let's say, and it's the same data, but it's totally different. And I just want to highlight that. And to fix that, it's a process called harmonization, meaning that we have to all agree that we're going to use a specific format. And then whoever doesn't have it in that format has to convert it into that format. So this is a good example of something very simple. You would imagine that blood pressure comparisons would be standardized and easy to do in data. It's not true. This is how one system would record a blood pressure as a string, as we call it. Nobody knows what I mean when I say string as a data type. This is a string. It's not something I can compute with a calculator. And this is a number. These are integers in a column, 4-column arrangement, where it's much easier. If somebody said, what's the average systolic blood pressure of all your patients? I could compute that here by one after another and just add them all up. Here, I can't. I have to actually write a program to parse this out into something like this. So when you have data from one hospital like this and another hospital does it this way, one of them has to change if you're going to do a computation that involves all the data. So that's called harmonization. To make sure that doesn't happen, everybody has to agree that this is the way we're going to do it. And if this is the way your system does it, you have to write a little program that before you give me the data, puts it in this arrangement. Okay. So the other thing I mentioned was coding systems that you'll encounter when we're doing things. Oftentimes we use codes. So we don't have we see the phrase pneumonia in the chart. The abstractor would have given that a code. And the traditional reason for that is also because when we send bills out to health plans or insurance, they don't want to see the string known as pneumonia. They have automation too. So they want to see a code, and then they go, oh, for the code XYZ, which means pneumonia, this is what I'm going to pay you. And that is a very common coding system called ICD, International Classification of Disease, is version 10, and this is CM. This is the system that we use in this country. There's a system for lab tests. So this does not include lab tests. This is just for diagnosis. So if I want to say, give me all the patients that have had a specific kind of lab test, like let's say I don't know, a PSA for prostate specific antigen. It's a screening test for prostate cancer. There's no way I could do it. I would have to find all the ones with a specific link code. CPT is procedural. So I want to find all the patients who've had an appendectomy or have been intubated or any procedure. That's the code that I'm looking for. And anybody who's on a specific medicine, I would look for codes in something like RxNorm. So I just want to highlight that what you're likely to see is not phrases and strings in the database, but codes that mean something. So this is just ICD. It's used around the world. Since we have a few minutes, I just wanted to kind of highlight the system is massive and it has some really ridiculous codes that actually are there. So I'm not going to go through them all, but like there's a code for being pecked by a turkey or walking into a lamppost or injured at an opera house. I didn't realize people get injured at opera houses. In an MMA fight, I could see, but an opera house, I don't know. This one was an interesting one. Drowning and submersion due to falling or jumping from a crushed fishing boat. Not an uncrushed one, but a crushed one. So anyway, have fun with looking at ICD-10. And what I do oftentimes is take the most ridiculous codes, and then I look to see if they're in there, because if they're in there, I know they're probably in there incorrectly. So it gives me an idea of how many errors might be in that data. And if I see somebody with this spacecraft collision injuring occupant, I don't think we have an astronaut as a patient, so that has been injured. So I would not expect to see that code in the system. The codes that I would expect to see are the standard, hypertension, diabetes, et cetera. There's a new system coming, ICD-11. It'll be here in probably 5 years. We'll start using it here. This CPT, just give you an idea, biopsies, pumps, and there's a code for each one of them. So just give me an idea. Loin codes are for lab tests. There's the loin codes for blood pressure. So there's actually 477 different types of blood pressure measurement. So you're probably asking, why blood pressure? Just one code, right? It's always done with the pressure cuff. Actually not. It's done with the pressure cuff, but then you do it every 8 hours, or is it the 1 hour one, or is it the 10-hour one, or and then is it done with a what we call an ART line, which is a pressure transducer in a catheter in the radial artery. And that's what we do in the ICU. So we have real-time arterial blood pressure measurements, because sometimes people get very sick and they become immediately hypotensive. You have to act or they die. So that's why we need that kind of a level of monitoring. So for the BME among you, that's something that in one class you might actually be asked to design one as an exercise. And then this is the ARC norm. It just gives you drugs and it tells you what kind of category they're in, et cetera. So you can do things like, give me all the patients that are on monoclonal antibodies, with a set of codes that way. All right. So oftentimes what you'll see now in healthcare is we have the data is coming out of a database, a data warehouse. The data warehouse data arrangement is typically done with a certain arrangement of tables, and people have created standards for those. And so you might go to an institution and they'll give you data out of theirs, and they're using a specific standard known as OMOP, and another one might use I2B2. So I just want to mention that those are arrangements of tables. Here's one called PCORNet. We don't use PCORNet here, but you'll see they're all pretty similar. Dispensing has to do with dispensing medications, lab result, diagnosis, encounter, pretty standard, provider, patient, that kind of thing, death cause. Here's I2B2. Here's observations or things that you observe or have, like you've recorded, like lab tests or vital signs, et cetera. And then here's patient, visit, provider, et cetera. Kind of the same kind of stuff. Here's OMOP, as I mentioned, observation medical outcomes partnership, person or patient. Drug exposure means how long was I on a drug? That's what that means. They even have a place where you can put note, the output of NLP, observations, just like I2B2, et cetera. So these are just arrangements of tables. So I'm going to show you something real quick here on arrangement of tables. And then there's a data set that we did on COVID here that's available to students. You don't have to get IRB approval to use it. You can only use it in a specific environment, which I'm hoping to log in and show you. We have 500,000 patients worth, 61 million observations there, 17 million clinical encounters. This is patients. This is just the COVID patients, not COVID patients, but COVID tested. So, and we have demographics, diagnoses, medications, labs, et cetera. So this is the kind of data set that you would want to do some research with. That's, if you know what you're doing with some minimal help, you can do. So what do you need? You need a set of tools. Well, I'll call that the data wrangler tool belt. So you need a programming language, because sometimes you have to manipulate data. Hopefully not, but Python's a great language for that. I think most of you likely know Python for one reason or another. Many of you have engineering backgrounds. Those of you who don't, Python's a very easy language to learn. You need a way to store data, manipulate it. I would recommend a database management system like Postgres. And then you need a place to do analytics, like analyzing the data. RStudio, and R is a statistical analysis language. Again, it's a programming language. A lot of stuff you can do in R, you can do in Python, but R is just simpler, and I'll show it to you. Often you need a tool to connect to the database and do queries and get the data out. You can either do it with the tool that comes with the database like Postgres, or there are tools that will connect to any type of relational database you have. This is meant to be SQL. And an example is Data Grip or SQL Workbench. And then it's always nice to have some test data. So there's a data set of real data out there that's been completely de-identified, but it's real data. That's about 12 years worth of ICU patients, 46,000 or so. And it's about 10 years old, but the data is there. It's all their labs, even their clinical notes. And of course, you need something to stay awake. So, I would recommend an espresso machine if you can afford it. This is Python. I think most of you have probably seen Python. It's an interpreted language, very simple. It reminds me a lot of C, original C, with the additional, ability to do a few things like it's more object oriented than the original C, so it's nice. The cool thing is that there's lots of packages to do all sorts of stuff that you don't have to write yourself, that you just import and use them. These are libraries, including the NLP libraries, so very helpful. Here's an example of a visualization library. So not just, that also allows you to grab data from a database and manipulate it in a tabular fashion in your program. Very useful. Here's some example of the code to do that. This is just an example of code for the Mimic data set. It's using something called a data frame. So that's a very commonly used term for the sort of tabular representation of your data in Python or whatever. R actually uses the exact same naming, and it's a tabular way of manipulating data. And these are all the visuals you can see. I mean, it's just very super cool. You don't have to write a program to do pie charts. You just import the library, have the data frame, tell it what you want it to do, which rows and columns, and then it produces the output for you. And that's very helpful to see stuff like this. So R is similar to Python. It's an interpreted language, but its syntax is very different. It is a statistical computing programming language. So it's an engine that does statistical computing, but it does, standard computation, if then else loops, things like that. It has arrays, but it'll do matrix, there's a lot of stuff in Python you can do. It's very equivalent. It's just different. And it's free and open source, just like Python. It's an interpreted language, so you can step through it. Has a lot of packages, broadly used. ggplot being one of them. So this is ggplot output from just that one statement here. It's give me the data and then just put it this way. One line of program, or a couple lines of programming did this. You can change the color, you can change the bars, you can, by just changing one piece of code. Super easy, but then you can see stuff. So you're not just querying the data and getting tabular output and going, gosh, I wonder if that's right. You get to see it visually when you're trying to check the data out. That's a very useful thing. So R and ggplot2 are your best friend for that. They're super simple. RStudio is just an integrated development environment to run R. R is actually command line. This is R actually running. Oops, right here. This whole thing here is a screen capture of RStudio. So here's, I did my programming, so it has an editor. And then as I'm stepping through, it's actually giving it to the engine to do the commands. And then whatever output from the engine that's graphical, it puts over here. So super helpful, just convenient. So it's just a convenience more than anything else. Here's an R code snippet. You can connect the databases from R. So there's a driver and there's a way of doing that using a library called DBMI, and then with the appropriate connector for the right database you have, in this case, Postgres. And this is just connecting to it. You'll notice you don't see the password here. You can actually tell it not to store the password and ask for the password every time. There's actually a code repository specific to the Mimic data set where people have done examples like the one I'm going to show you. So you just look it up as Mimic 3 code, code repository. And then Postgres, like you don't have to store the data in a database management system yourself, but it's highly advisable. You can certainly open the files natively and do things with Python, but pretty quickly you're going to want to put lots of data in there and do queries to get subsets of the data out. Nothing better than the database to do that. And I think, you've been exposed to, that's what we're trying to expose you to. So I'm not focusing on the database per se today. I'm showing you how it's used in the ecosystem and for research purposes. I like Postgres, as Lauren knows. It's simple, it's open source, it's very functional, it's highly mature, it's 25 years old now, meaning it's been updated and evolved for 25 years. We're not using 25-year-old technology. It comes with a nice client, which I'll show you. And it actually got the Database of the Year award last year. So beat Oracle, all the commercial ones. Running Postgres, you can either run it on your computer yourself. You can actually download it and run it on Windows, Mac, etc. And you can load data, and it's running a real server, on your laptop or whatever. You can run it in a data center, which most of you are not going to have the opportunity to do, or you can just spawn one on Amazon Web Services, which is a commercial cloud environment, which is what I've done, and I can show you this, what we're going to connect to here in a second. You can, like I said, you can access Postgres from R using that library interface and putting it all together. This is what I'm just going to demonstrate to you, and highlighting something on as kind of a data quality aspect, or data profiling as we call it. So before I get to there, I do want to highlight interesting publicly available data sets. Where should you go to just browse for that? There's a movement called the Open Data Movement, which started with Todd Park, who was actually a developer of an EHR and a billing company system called Athena Health out of the Bay Area, him and his brother. And Todd Park was actually knew Obama and was hired to be the chief technical officer of the Centers for Medicare and Medicaid. And later he became the CTO for the White House. And Todd, he's very pragmatic. So he said, he landed there and is like, it's a huge place, right? He said the one thing that would impress him the most was how much data the Centers for Medicare and Medicaid had that would be useful for researchers like us and others and policymakers, that was very hard to get to because you had to know who had it, et cetera. So he kicked off this movement called the Open Data Movement, where let's put it all on portals that people can download easily and find the data sets and then get access to them. And that caught fire. So there are open data portals for the federal government. There's actually one in California. So this is California Open Data. So any data that you might want to find, go there first. It may be an Excel spreadsheet, it may be PDF, but it almost always it's structured data that you can then take and put into a database and do some manipulation with it. There's tons of data sets in there. For example, just as an example, vaccination rates. They update that data file every 2 days. So if we wanted to know what the vaccination rate is for every county in California as of 2 days ago, we can just go right here, go into that. In fact, oftentimes you don't have to download it. They have the thing that says, let me show it to you, and you click it, and it's basically doing a visual, computation for you on the system. So your tax dollars at work. This is Open Data Portal at the federal government. It's data.gov. Same idea, but you'll notice 319,000 data sets, and you can search them. So there's all sorts of stuff in there. And then there's CMS. This is Centers for Medicare and Medicaid. So if you want stuff directly about health, CMS as a health plan, basically Medicaid, Medicare, you would go here. Medicaid spending by drug, Medicare Part B spending by drug. You want to know how much we're paying for, I don't know, some sort of drug that's being prescribed and billed to Medicare. You would download that data set, you'd know in minutes. Okay, unprecedented access to data, all because of Todd Park. And then this is the kind of stuff you can do from it. So I'm just going to stop here. I know we are almost at time. For 3 minutes, it looks like. So I happen to have queued up my RStudio. So here's the RStudio code. It is not hard at all. This is just loading libraries. Here's setting it so that it actually provides me enough memory, because when I load this, it's going to be 56,000 rows. And that this is set at 1,000, because R itself is memory resident, so it doesn't want to kill your computer. But my computer has plenty of memory. So this is the connection, parameters. And then this is it connecting. This is the query it does. The SQL is a little complicated, but not bad. So I'll show you, what it's going to do. And then it does the plotting. The plotting it looks complicated, but it isn't. These are the tick marks. So notice the tick marks over here are actually much more close, and the numbers kind of go over each other. That's because of what I did over here. So I could just go and make this a different tick mark. So what you do is you just go like this. I could do one by one. I could just start here and say run step by step, click, click, or I could just go here to be very quick and just say run the whole thing. And now it got to, hey, I need your database password, right? So now it's running. Here's the output of the data, and now it's plotting it, and here's the output. So here's a histogram, the one that I showed you before. That was a screen capture. I'm gonna run that now. There's the histogram. Okay. So I want to get back to this one. So I'm going to run this one, and I'm going to ask you a little mini quiz question, which Lauren, I'm sure knows why I'm asking this. Why I'm going to ask this observation thing. Is there something weird you see in this picture here? Weird, meaning, does it look like a normal distribution of ages? This is age, number of people at a certain age. So this is 15 years of age. Here's 0, 15, here's 90.
Like, are you looking at the distribution or the age
Yeah.
limit?
Well, just look at this for a second. What's odd about it? This right, even just this right here.
It's skewed towards older people.
It is, but don't you notice this right here? Like there's, it chopped it off. You see that? There's nobody older than 90. That's weird, right? See, it's like it chopped it off right here. Normally you would expect this to be skewed like you're saying and have kind of a, what we call a Gaussian distribution, this sort of bell-shaped curve and come down here. And maybe there's somebody in here that's, 100 years old, maybe a few, but there's nobody over 90. It's as if it got chopped off. Does everybody see that? It got chopped off. So you're like, is that for real? And I'm looking here. So here's the actual raw data. Okay. Over here, I'm scrolling up. Okay. I'm scrolling up. As I scroll up, is there anything that catches your eye? These are patient IDs, and these are their ages. Anything catching your eye? There's two that catch my eye right away. You see them?
200 or 300 years old.
Exactly. Now look over here. Do you see something odd that you probably missed in the picture? You see this line over here? You see there's a little slight yellowness here? This is 300. So yeah, there are patients in that data set that have a year of birth that makes them 300 years old. Imagine if I had not done this and I did a survival curve, it would be wrong. Why are there patients in there with 300 years of age? Notice it's 300 exactly. 300 exactly. It's not 301. It's not 302. It's 300. Why do you think that might be? It could be a mistake, right? Could be a mistake. But so we do see two things that are odd. It chopped it off here, and I have a lot of 300s. Okay. This does not come with the data set. This explanation does not come with the data set. So if somebody used the data set without understanding, when I said you need to know the domain a little bit and the computer science part, but I'm trying to find one that's almost 300. There are a few in here that are a little bit more than 300. Why do I know that? There's a slight yellow tinge here. You can't really tell, but so it's not just 300, 300, 300. There's a few that are like 304, 305, 309, but there are very few. It's a very odd thing, right? So here's some more 300s. I'm trying to find one that's not really 300. They have to be in here, but I'm scrolling pretty fast. So I'll tell you why. So when we try to preserve data for privacy purposes, preserve privacy in healthcare data, there's a law called HIPAA. HIPAA says you can use healthcare data as if it were not healthcare data only after you do de-identification on it. They stipulate what you need to do to de-identify. You have to take all the identifiers away, but you also have to you have to lump together anybody who's over 90. In other words, anybody over 90, if they're 95, you have to make them a lump in a single digit because there's so few, so that there's a risk of re-identification. So they took everybody who was over 90 and made them 300 is what they did. That's what they did. So I went and asked them, is that what you did? They said, yes. I said, you should probably put that in as a little footnote somewhere in the file. But this is why you do what I just talked about. You're a data wrangler. You go, whoa, that's what. So that explains that. Notice there's nobody less than 15. That's it's an odd age, isn't it? 15. 15. There's nobody from 0 to 15. It turns out that there's an ICU, pediatric ICU. They excluded all the pediatric ICU patients, but they did it by location. There were 2 pediatric patients, or a handful, that were actually below the age of 16, and they should have been in the pediatric ICU, but they ended up in the adult ICU. Why? Because they were in a rollover car wreck. And and that's where they ended up, and they didn't want to move them until they were better. Once they got better, they transferred them to the pediatric ICU, and then their data disappeared after that. But they're like 2 or 3 days worth is in there, so that's why you see some that are actually, you would expect not to have them. So again, that's not in the explanation for the data set either. So this is why you explore that kind of stuff. So before you use the data to do any statistic, that you want to kind of get an idea. This is called data profiling. The only way I would have, I discovered this way was doing this with this tool. Able to access the database. Yes, I'll put, and I saw that and I was like, that's weird. Why did I see it's de-identified. What is that line about? Because I didn't tell it to make a red line there. I didn't program it. It is real. It's the data. And I was like, oh, maybe it's a mistake. And then I started looking at the data. Yeah, it's there. It's 300s. And then when I emailed them, I said, yeah, we made everybody over 90, 300 years of age. And I was like, okay. They were, the reason they did that, they wanted to make it an obvious error. And it didn't work because I looked at it and it was wrong. Right. As opposed to making everybody over 90, 91. There, then it's harder to detect. It's like, well, wait a minute. All of a sudden I've got this thing here. People might not see that or perceive it. This definitely perceptible, but only if you make this 300. So if I go over here, you notice it says scale Y contiguous, scale here to 120 or something. But then there's this over here. So it automatically didn't cut it off. But if I went like this, you'll notice if I go 300, it's going to add a tick mark out there. So we can see exactly whether it's at 300 or not. It should.
Dr. Hogarth, what did you
Yes.
do when you needed some kind of summary statistic, like median age or whatnot? What did you do with all those 300 patients?
So you would want to exclude them. So when you do the query, so I can do that right now. I don't have it set up to do median age, right? But what I notice here, it says, this is the query. The query, the SQL query is select the individual's ID and get their age, their year of age, their total years of life, from the age at admission. That's what this is doing. From the patient table, join it with the admission table, where I can get the admission time and all that stuff. So I know the age when they were admitted. So notice it says greater than 0, less than 400. Notice it says greater than 0. What if I say I get rid of this right here? Okay, so I'm going to do 2 things. I'm going to make this go less than 120. So I'm doing this in real time. This is the beauty of an interpreted language. So now it's going to run. And you should see it disappear. See, it's gone. See that? So when it plotted it, it did not have 300. And in fact, it ignored my command to give it a 300 tick mark because there's nothing over there. So this plotting visualization library is pretty smart. You see, but I got rid of it by just changing the query here. The age parameter, I said, don't give me anybody give me only people that are between the ages of 0 and more than 0 and less than 120. So what is it doing? It's actually also giving me people that are over the age of 0, right? We know people are age 0 when they're 1 month, 2 months, right? There's a neonatal ICU. So there's neonatal ICU, pediatric ICU, and adult ICU, right? Because I'm a domain expert, I kind of know that. That tends to be the arrangement. So let me do this. I'm going to get rid of...
Dr. Hogarth, sorry to cut you off. We actually have our next speaker that we need to start soon.
Yeah.
But if you have a couple more things you want to run over, then great.
I'm gonna just run this way.
Cool.
So because I want to show you one last thing. Notice what happened.
Lots of zeros.
Well, what happened? Exactly. Lots of zeros. And this became smaller, but there are neonates in here. They're neonatal ICU patients. So when I said greater than 0, I was actually excluding them. So I took that clause part away, and now they're here. So if I did this, 400 now, if I just did it this way, go back to that 400, and then we'll be done. What do you think is going to happen? You're going to see 2 red stripes. So now we know the data set we have a little bit better, right? It would be much harder if you didn't have that capability. And you'll notice that the neonatal ICU, the number there is much higher. So this has a lot of data from neonates, this data set, you see that? There's a lot more neonates than there are over 90s. So anyway, so there's lots we could do. So I just wanted to kind of, hopefully that was a whirlwind tour. And if anybody has questions or whatever, you know, send them along by email. But I would recommend you request access to Mimic, which you can do on your own. There's a process for applying. They'll give you access to the data set, and you can download the data, load it into your own database server, or you know, Postgres on your computer. Do RStudio the same way I did, and do this kind of stuff. And then you're off to the races as data wranglers. We're not going to furnish any cowboy, you know, uniforms or anything for data wrangling, but you're officially now anointed junior data wranglers. All right, I think we're done, unless folks have any questions. And sorry, I went past time here.
No worries. It's always very interesting. Thank you
All
so
right.
much, Dr.
Okay.
Hogarth.
All right, you bet. Take care. Bye.
Bye.